local expert. Thank you. In confinement, not part of our collaboration, so it's important that collaboration hear from them and get advice. But let me start out with so the idea is that I'm going to say a few remarks, and then Juan, Nadi, and Edward, in that order, will give short presentations, 10 minutes-ish, right? Something like that. And I actually asked them some questions, but hopefully they'll have other questions for which they know the answers. And but before I go to that, let me say a few words about this collaboration and the Simons Foundation and some historical remarks. So unfortunately, all the Simons people have departed, right?
Some of us are on Zoom.
Well, we first I wanted to thank you and for supporting this collaboration, but much more broadly for really doing what Simons has been doing for the last few years, increasingly so, in supporting theoretical physics, theoretical sciences in general, but I know mostly about what they've done in physics. And I regard it as quite remarkable and incredibly important for this field, especially since they do it so well. Not just because they chose this collaboration, but they've had extremely good taste and really have made a big impact in the areas they have funded. And so thanks and congratulations, and keep it up. Given the present state of our government and our funding situation, I can only imagine what the state of theoretical physics in the US would be at this point, without the Simons Foundation and their efforts.
Thank you very much, David. I will convey to the leadership.
Okay. Yeah, and you really should thank Jim, because he really set it up, and I've had some experience with raising money from foundations, and Simons really stands out. I mean, it's amazing. Okay, so confinement. So I'm going to go back a while. You've heard a bit from people who were around 50 years ago. But confinement's an interesting problem since we all believe in confinement. And actually, I think the word was conceivably introduced by Gell-Mann when quarks were thought of as really a mathematical device for classifying flavor symmetries. And then it was a mystery. Why, there was no sign of quarks. Of course, that is the reason we truly believe that confinement is correct, that QCD confines quarks. In the end, it's experiment. Physics is an experimental science. And even back before QCD, before there was really any kind of theory, just patterns of symmetries, the idea that the basic building blocks of flavor symmetry would be not produced in collisions, you couldn't ionize hadrons, seemed extremely strange. And it was one of the reasons nobody took quarks very seriously as dynamical objects. But the evidence, from my point of view, the evidence for quarks became very compelling, as well as their identification as point-like partons or constituents of of protons with the slack deep inelastic scattering experiment, which was, in effect, the pivotal experiment that in the strong interactions. So that is now 55 years ago, and it was quite stunning. And there were really these two aspects to it. One, the scaling of the cross-sections could easily be explained if the constituents of proton were weakly interacting, which seemed bizarre, and but more specifically that they had the quantum numbers of quarks, or the properties that were assigned then to quarks. Initially, the spin of the quarks, baryon number, charge, and then color. And so it was really that experiment that gave rise to two problems. One is, how the hell could the proton be made out of non-interacting point-like objects, and which look like quarks? And second, if it's made out of these weakly interacting at short distances, but not that short. I mean, the slack experiments were at very low values of q squared, and remarkably already showed this behavior. Where were the quarks? So the short distance and the long distance behavior of hadronic physics was evident in these experiments. And personally, I was focused on the short distance behavior, which seemed like something that one might try to explain, and was led within a few years to asymptotic freedom, to QCD. But the other problem of why you don't see the quarks was always there, and was the first thing that after you realized that given the scarcity of asymptotically free theories, which really were necessary to explain deep inelastic scattering, had to be then demonstrated in this theory. And from the beginning, I kind of felt that unless one could solve the problem of confinement, one really couldn't claim that QCD made sense as a theory of hadronic structure. However, that concern was dissipated or relieved for many reasons. First and foremost, of course, was experiment. So experiments were performed at ever-increasing energies, no quarks, except 1977. So those of you who weren't born then perhaps don't know that Fairbanks discovered charge 1/3, 2/3 particles in the oil drop experiment, which you all might have done in undergraduate labs. As you know, it's a very difficult experiment to do, and you probably experienced the fact that since you knew the charge had to come out to be an integer multiple of E, you tended to bin things so that. And so did Fairbanks, or his students and postdocs. But he had extraordinary 5 sigma, he had 10 sigma, 20 sigma evidence for sharp peaks at 2/3 and 1/3. New York Times article, evidence for the existence of 1977. By that time, most of us knew that this was garbage. there's an interesting story about that. So sometime around 1978, 79, Louis Alvarez, a particle experimenter, Nobel Prize winner, great physicist, visited Princeton. And I was lucky enough to go out to lunch with him at Prospect with Val Fitch. And he said, I had to tell you this story. He was talking to Val. I was really angry. He was angry with Fairbank. Why? Well, he was Alvarez was very interested in looking for quarks, monopoles, all sorts of exotic hypothetical particles. So he was very interested in Fairbank's result. And he went out and visited his lab. Fairbank showed him, well, these were superconducting droplets of
niobium balls.
niobium balls, right?
There's a T-shirt.
Which says,
It takes niobium balls to discover quarks.
right.
It disappeared from the market.
Of course. So anyway, Albert went out and visited Fairbank's lab, and he was shown around. All looked very impressive. He was a bit suspicious of the atmosphere, the culture in the lab among the young researchers who were actually doing the work. So he suggested Alvarez was going to have another run and get more statistics. And Alvarez said, why don't you do a blind experiment? And he said, what's that? He said, well, I'll send you a random number generator. You simply add it, mod 1 to your data. And then at the end, after you control all the systematics and do all the analysis, I'll send you the key. So that eliminates unconscious or conscious bias. So he did that. Alvarez said, that's a good idea. And he agreed. Alvarez sent him the random number generator, did the experiment, and at the end, turned the key. Nothing. Noise, peak at 1, mod 1. That's it. Fairbank never published that negative result. And Alvarez was furious. And so he went around telling people this story. And it's a very good lesson because there was no fraud. It was just unconscious bias. So for example, we all want to prove confinement. We know what we want to prove. Experiment tells us. We have unconscious bias. However, we have ways of called meetings like this where we can check. We don't actually insert random errors into our lattice calculations or things like that. Anyway, going back to the early days, I thought that the main challenge was to show that it made sense to talk about a theory of hadrons made out of quarks held together by gluons, but where you never saw the quarks, asymptotic states. And believe me, most of the community thought this was crazy. I used to have big arguments with Eugene Wigner, who was a very polite, great physicist, just explaining to me that the only particles that make sense that you could possibly talk about and write theories of are irreducible unitary representations of the Poincare group. And if there are no asymptotic states, they don't exist. Anyway, what made me feel a lot more comfortable in the rapid developments of 50 years ago was a whole bunch of things. One was, well, for me, partly the work with Nouveau on an asymptotically free model, which could be solved in the large N limit and showed dimensional transmutation and a mass gap. The Hooft model, a large N two-dimensional gauge theory, which again was soluble, so you could exactly understand how confined quarks could be seen at short distances as they are in QCD, but still confined. The understanding that they're analog, there are analogs of quark confinement in QCD and magnetic monopole confinement in ordinary superconductors. The three-dimensional compact QED particle model of confinement, monopole condensation, and much later the N equal supersymmetric Seiberg Witten similar confinement model in 4 dimensions much later. And in general, the large N and the beginning of the realization that QCD should have a string theory description, et cetera, et cetera. But confinement was and continues to be a very hard problem because there's no obvious small parameter which one can calculate, except perhaps for large N. And inspired by Sasha's work on compact QED and the realization that one could get interesting non-perturbative dynamics semi-classically by including the contribution of non-trivial, topologically non-trivial contributions to the path integral. Kurt, Roger Dash, and I spent many years trying to apply those ideas using instantons and eventually fractions of instants to try to construct a quantitative approach, a semi-classical kind of expansion to QCD. Many of the ideas I just mentioned have survived and continue to be part of the way we might solve the problem. Now, what does it really mean for us to, what would it mean to solve confinement? That's one of the questions I asked these experts to comment on. One of the solutions, I suppose, would be to prove confinement. And indeed, Edward is the author of the Clay, one of the co-author of the Clay Prize, which would give $1 million to anyone who proves the existence of a mass gap, which is perhaps a somewhat easier version, but if you were to prove a mass gap for QCD or for a non-abelian gauge theory in general, confinement is bound to be a consequence, I would think. But I don't think that's why most of us are interested in understanding or proving confinement. For me, always solving the confinement problem was more developing an analytic pencil and paper, back of the envelope way of calculating say, the mass spectrum of QCD. We have calculated, or the community, lattice gauge theorists have calculated the mass spectrum of QCD, dozens of particles by now, with less than 1% accuracy. It's unbelievable achievement. Very pleasing to see this. Quite amazing. But still, we would like to be able at some point to do it analytically. Plus, their analytic control over confinement, we believe, would allow us to approach many other aspects of QCD which are not understood. We heard today the story of the Pomeron of diffraction scattering. That is a very difficult problem, which almost not much has been learned in the last 30 years, 40 years. And lattice gauge theory so far is unable to tell us almost anything. But in addition, for many of us, certainly me, the understanding confinement is closely related to understanding better string theory. And here, of course, there have been many advances in the last 50 years, so that we have, I think, a reasonable hope of understanding perhaps both confinement and non-critical string theory much better. So we've heard during this meeting a lot of wonderful new-ish ideas, in addition to the old-ish ideas, which give us hope, and one of the motivations for this collaboration, that this is a good time to return to this 50-year-old problem and try to make significant advances. And I think that's the case. The stories we've heard about the effective string theory, the worldsheet dynamics along confining string, especially n equals infinity and no quarks, I think offer much hope that that could be understood within the framework of this collaboration. And it can, although that's, not exactly QCD, its predictions, that understanding can be informed by and tested by lattice gauge theory. We've also heard about the new developments in understanding ADS-CFT duality, which gives a string theory, you want of supersymmetric gauge theory, and for weak coupling in a very precise fashion. And that offers the hope of, if that can be really pushed much farther to deform the string theory of supersymmetric gauge theories, which is not confining to QCD. Then, of course, there have been enormous advances in lattice gauge theory, which we heard about, which are remarkable, and we have, sounds like, promises of continued exponential growth in our ability with new methods, perhaps eventually quantum computers, to get theoretical experimental input into our understanding of strongly coupled gauge theories. And I think especially those three developments are very exciting. And together with all the other information that other advances that have been made in understanding quantum field theory and string theory over the last years, give us much hope that breakthroughs can happen. They will undoubtedly involve new ideas that haven't been talked about yet because they haven't been produced, and most likely they will not be produced by the old experts, the older experts, but by the younger, not yet experts. This is so finally I'm just going to end briefly with a pitch to some of the younger people here. It's not a bad subject to move into if you find it interesting and you might like working on this kind of problem for a variety of reasons. One, it's a very important problem. Two, not that many people are working on it. Three, it's really ripe for new ideas. And so it's risky, much less risky to do what everyone else is doing. Because then at least you have somebody to talk to about it. But the payoff is much larger if you go into a new direction. So think about it, follow the great advances that we intend to make, and join the effort. Thank you. And so we're now going to hear 10-ish minutes from each of our local experts, and then we'll have a more open discussion question period. So our first speaker is Juan. Here.
Okay, thank you. So what is confinement? Well, it's a very fundamental feature of nature, and we should understand it. And it really answers Pauli's objection to Young and also to Mills. You probably know the story of the seminar that Young gave at the Institute, and Pauli objected because he said this theory cannot make sense because it predicts massless particles. And Young didn't know what to answer. He kind of was embarrassed and said, well, it's a difficult problem. I'm not sure why he thought it was difficult at the time. Because if you, no, in the sense that if you naively expand this Lagrangian at the level they were doing things at the time, you would naively have concluded the same as Pauli. But yeah, of course, this is one of possible answer. Of course, we know the other possible answer, which is Higgs, the Higgs mechanism. But well, so one of the questions was, what's the status? And one question is, does it happen in QCD? And I think we really know that the answer is yes from numerical calculations. Can it happen in other models? And we know, yes, from many other models, many other examples that it can happen. David mentioned many of them, which are including in 4 dimensions with special matter content, with supersymmetry or large N. Now, one question we can ask is, what does it mean to understand it? Well, one question is whether we have a simple conceptual picture of why it happens. So does it happen due to some particle, to some defect? Does it happen due to instantons or other objects? And in many examples, we can understand it as a consequence of some objects, like the 3D case, the Polyakov example, or the SUSY case of Seiberg and Witten. Now, a new recent idea is the idea that we have generalized symmetries, one-form symmetries. Maybe they also, and we know that they are restored in confinement, but what causes this, or how do we understand it more precisely? Now, I think I suspect that these simple conceptual pictures are sometimes possible because there is an underlying dual, perhaps in some dual variables, weakly coupled description. But I suspect that that would not be the case for QCD for Young-Mills, for the Young-Mills theory we're really interested in. Now, another possibility is to say that we prove it mathematically. And well, that's certainly one possibility. But sometimes we would like to understand when it happens. So for example, we like to explain where is the edge of the conformal window as you start increasing the number of or decreasing the number of quark flavors. Or also, well, David mentioned that we would like to have perhaps analytic methods for finding the spectrum. That looks like a tall order, but well, I suspect that an exact solution is unlikely for, but maybe prove me wrong, please. And the lattice is currently the best tool to find the spectrum. But there are new ideas, and one idea is the idea of the S matrix bootstrap. There's been tremendous advances in this bootstrap technology for other problems, and this might be a problem where we would perhaps get the spectrum using a combination of some version of numerical bootstrap. And many people are exploring this. Another possibility is to solve the theory at large n, we know that we should have free string theories at large n, and we would like to find the string Walsh theory. And even if we cannot find it analytically, perhaps we could analyze that two-dimensional field theory numerically. So that would be a possibility. And one interesting aspect is this idea of loop equations to get expectation values of various Wilson loops. Sasha talked briefly about that. And this is one of these ideas that did not work in the past, so because people could not solve them somehow analytically. But it might be that with numerical analysis, it perhaps could be solved. So problems that a long time ago could not be solved now, with new numerical techniques, perhaps we can solve them. Let me say a few more words about why I think this is a problem that perhaps can be solved. So we're interested in considering Wilson loop expectation values on the lattice. And in fact, we can write down these loop equations, and these are equations we write down at large n. So for n equal to infinity, the equations are independent of n, so they constrain the expectation values of these Wilson loops. There is an infinite number of variables, which are all the various expectation values. And some people, so there is actually recent papers that solve these equations assuming certain positivity conditions, so kind of similar to the bootstrap techniques applied in other contexts. And we can think of them as wave functions of the string Walsh, or wave functions roughly on a spin chain, where each of the sides correspond to a decision of whether in the loop we go up or down, or left or right, etc. So, and for this type of problems of 1D wave functions, there's been a lot of progress using, for other models, using either tensor networks, the MRG, or machine learning to learn these wave functions numerically, and perhaps this could be a way to solve this problem. Of course, at my level of understanding, I don't know the big difference between all these three words. The specialists think that they're all very different. What?
Machine learning starts with data.
Well, the idea, well, okay. The idea is that you want to impose some equations, and so you could try to guess the Wilson loop expectation values, and then define a loss function that is that equation, and then you just do gradient descent and try to find those equations. You have to represent the vectors in terms of a tensor network or a neural network, and then you would apply this. You try to minimize. So machine learning minimizes a function, and so we have a different function. That would be an idea. I don't know more than this, so hopefully some of you might figure this out. Another possibility about large n is to try to solve the n equal to 1 supersymmetric Young-Mills. This might be an intermediate case between the, let's say, n equal to 4 supersymmetric Young-Mills and the n equal to 0. There are some non-critical backgrounds where if you put branes in those backgrounds, you have literally n equal to 1 super Young-Mills without any extra matter. And if we could understand the back reaction, we would get the dual. We don't know how to deal with this back reaction in such cases, but it might be doable. Okay, that's all I was planning to say. Thank you.
Next speaker is not instructed.
Let's check here. One thing.
Yeah.
Okay.
Now let's see if I can share the screen. First, the whole window. Okay, I'll do this. No, but then it will not share correctly. This is the same problem we had before.
Share that.
I'll just share the screen.
Or the presentation.
Share the presentation. What does it do in the Zoom? Yeah, that's what I don't want.
Yeah.
I'll share the screen. But I don't want to. How do I remove the other screen? I don't want the presentation mode. That should work. Okay. Okay, so I want to thank you for putting together this meeting and for inviting me to speak here. More importantly, I want to thank the Simons Foundation for supporting this collaboration and many others. I also want to congratulate the Simons Foundation for making these correct decisions how to fund science. This was clearly a good choice, and I hope they continue to do that. I hope Greg is still there to hear these things.
Yes, I'm here. Thank you, Nari. Appreciate it.
So we were asked to talk about confinement, and honestly, I don't have much to say. So I'll repeat things that people have already said here, and hopefully this would stimulate some discussion later. So the first question we would like to answer is, what is confinement? And it's actually not as simple as people might think. The original answer, as David said, is this is the statement that there are no isolated quarks, except I think there were a few events in California that David mentioned. And there's a more sophisticated answer, is that all the particles in the spectrum have integer baryon number. I'm using normalization where the baryon has a charge a third. This is a more sophisticated baryon. Then the issue was electric charge, but we might as well talk about baryon number. And there's an even more sophisticated version that the theory has strings. And we've heard a lot about the idea that the Wilson loop exhibits an area law. So these are various definitions of confinement. However, there's something uneasy about it because we all know that pair creation of quarks can remove the string. And therefore, what does it mean that QCD confines if we don't really have strings in the end of the day? Correspondingly, the Wilson loop has a perimeter law. That statement was made more precise in beautiful work by Fratkin, Schenker, Banks, and Rabinovich. These are two separate papers. And they basically claim that if we have quarks in the fundamental representation, there is no real phase transition between Higgs and confinement.
More precisely, there could be a phase transition, but we can continuously connect one to the other. So if we want to prove confinement, maybe we should prove that QCD has a Higgs mechanism. That doesn't sound right. There's a more modern version that also people alluded to here, that if there are no particles in the fundamental representation, the theory has a one-form global symmetry. And confinement is a statement about symmetry, so this is much better. We know symmetry is or is not spontaneously broken. This is the statement that the one-form global symmetry is not spontaneously broken. And we can refine this statement better by talking about other groups and taking quotients of the group in different representations, but let's not get into this fine print. So with quarks in the fundamental representation, there is no such symmetry, and therefore confinement is not well defined. So this could be a summary of this discussion. But let's go back to the baryon number criterion. This particle that was not found in California. So is it or is it not a good criterion to say there are no particles with fractional baryon number in the spectrum? That's a question that I would like to address. So to be concrete, let's consider SU3 gauge theory with quarks in the fundamental representation with the baryon number a third to them. And then it's easy to see that all the gauge invariant operators have integer baryon number. I can say it in a fancier language, but that's kind of obvious. And then we can ask, is it even in principle possible to have particles with fractional B? Is it possible at all? It turns out that if you think a little bit about it, the only way to get particles with fractional B in the spectrum is if the low energy theory has gauge fields. So we can have gauge non-invariant particles only, so in order to have fractional B, the particle has to be non-gauge invariant. And this is possible only if we have gauge fields. So we have electrons in the world because there is a massless photon. So these two things are correlated. So here is an example. Let's add an adjoint scalar to the theory. We can use the adjoint scalar to Higgs SU3 to Z3. And then indeed, the theory is not strongly coupled because it was Higgs. And now we can have quarks, free quarks, and we have particles, asymptotic state particles that maybe Wigner would be satisfied with, particles with baryon number a third. And that makes sense because they are attached to Z3 Wilson lines. And therefore it makes sense that they have fractional charge. In fact, we've already seen exactly this mechanism in the lab in the fractional quantum Hall effect. We have fractional charges because there's an emergent Z3 gauge theory in Laughlin state. So things hang together. However, we cannot have particles with fractional baryon number in a trivially gapped phase. So now I'm refining the statement. We need to have a gap in the spectrum. And furthermore, there shouldn't be any gauge theory or a topological field theory at long distances. The theory has to be not just gap, but completely trivial. Otherwise, we cannot get fractional charges. So the question is, so now that we have a more refined version of the question, we can ask, does a trivially gapped phase in QCD mean confinement? Are these two things the same or not? So I'm going to present a model that kind of addresses the question. Let's take the same old QCD and throw in a scalar field S in the 6-dimensional representation of SU3. You can think of it as a 3x3 symmetric complex matrix. And it's such that it can couple to a fermion bilinear, and there's also some potential. And since what we're talking about is baryon number, let's impose baryon number. So the quark has charge a third, and therefore S should have charge 2/3, so that S bar has charge minus 2/3, and we can impose the baryon number symmetry and the potential. So this is a nice model. It has baryon number, has SU3. All the gauge invariant operators have quantized baryon number. So this is a good model for QCD. This is not QCD, this is QCD prime. But as far as addressing the question, we can ask the question here about the role of baryon number. So phase number one, the potential is such that the minimum of the potential is at the origin and S is massive. So S is heavy, and at low energies, what we have is exactly the same as QCD. This whole added particle doesn't make any difference. And the theory, quote unquote, confines. This is the theory we're interested in. And now we can ask, can we really say that this is confinement? So I'm going to change the parameters, change the potential, and change the potential such that S gets an expectation value. So imagine the expectation value of S is a diagonal 3x3 matrix with two non-zero entries and a vanishing entry. So this S completely Higgses the SU3, so the SU3 is completely Higgsed. Baryon number is spontaneously broken because S has non-zero baryon number, but there's a combination of the flavor U1 and color, which is unbroken. So this system, SU3 is completely Higgsed. It's complete Higgs mechanism, no confinement, no strong coupling at long distances, and all the particles have integer baryon number. So all the quarks have integer baryon number. Well, that's actually not a new result. This is essentially a model by Han and Nambu, which was mentioned by Igor earlier in the conference. So the quarks have integer B prime. The spectrum has particles with integer B. And the spectrum is gapped. There's no gauge theory at long distances. And it satisfies the criterion of quantized charges. But that's not confinement. So in this phase, it looks like confinement, very much like in the real world. And this is clearly not confinement because the SU3 is weakly coupled, it's completely Higgsed. So this is clearly a Higgs phase. So I changed the parameters in this model. Baryon number is never spontaneously broken. All the particles have quantized baryon number, and I interpolated between Higgs and confinement. So I would conjecture that there is a continuous path without a phase transition, very much like liquid and gas, that we can go around and connect these two phases, because after all, they're both gapped. There's no low energy gauge field, so they're trivially gapped. There's no autoparameter that distinguishes between them. So I would guess that we can change the parameters and continuously interpolate between them, and thus have integer baryon number and confinement the same as Higgs. So as expected, there is no clear meaning of confinement in the theory with quarks in the fundamental representation, which was perhaps the prejudice that most of us already had. So going back to QCD, as we said, there is no rigorous notion of confinement as opposed to Higgs, but confinement is meaningful in various limits. So one limit is large quark masses. The quarks become heavier and heavier. They cannot pair create, and they cannot screen the string. Large N, at large N, the quarks are suppressed, although we heard a fascinating talk earlier today, kind of addressing precisely this, and I'm now a little bit confused whether this thing should or should not be there. I'm talking about QCD, the theory with quarks. Without quarks, there's no question. And we should put something for the nice challenge for the younger people in the audience. Find another limit where one can address this question in a systematic way. So what does it mean to prove confinement in QCD? I went through the questions that David sent me, and I scratched my head, so what does it really mean? I think that's what it means. We have to show that QCD with massive quarks, the quarks have to be massive because otherwise there could be massless Goldstone bosons, is a trivially gapped spectrum. So every element of this is important. So note it should be gapped, but also it should be trivially gapped so that there is no TQFT at long distances. And this would not quite prove confinement, but it will prove confinement or complete Higgsing. And there is no difference between them. So looking forward, I think that this is a fantastic question, confinement problem. And because proving that gauge theory is confined is interesting and important for several reasons. First of all, it's a concrete problem. I think this is a tip to young people, keep the problems concrete, because if it's not concrete, you get all over the map. Second reason, it's related to the real world. This is a phenomenon that we all know exists. And it's also a good question to focus our thinking about quantum field theory and more generally string theory, because having a concrete problem, even if we don't prove confinement, we'll learn something else which is interesting. And having such good problems is a good idea. So I have no doubt that work along this direction will lead to deep insights into quantum field theory and also string theory and its various applications. It's not just for hadrons, it's other questions in high energy physics, maybe physics of TeV, TeV scale physics, problems in condensed matter physics, cosmology, mathematics, and the list goes on. So because of this optimistic outlook, I would like to congratulate again the Simons Foundation for supporting this effort. Thank you. Yes, Greg, good to see you.
Always good to see you, Nari. Thank you.
Okay, we're gonna reserve all questions and the next speaker is up in bit.
Oops, yeah.
Even though the request to make remarks for just a few minutes was modest, I actually found it relatively difficult because I didn't have that much that was novel to say. And I don't know I would make some historical remarks, but David stole my thunder several times over. but I'll still make a couple. So I arrived as a graduate student a few months after the discovery of asymptotic freedom, but it probably was a year after that before I knew enough so that I understood the question of confinement. So let's say that was a year and a half after the discovery of asymptotic freedom. And I remember very well that it seemed quite bizarre and frankly hard to believe. But it also became an obsession. Throughout the 70s, I was totally obsessed with the problem of confinement. And I only gave up on that obsession because I couldn't get anywhere with it. So I had to do other things. Eventually, you have to do things you can do. There's something else you can do. But of course, by the end of the 70s, the picture had changed a lot. And if I look back, there are sort of, I'd summarize it as three developments that made confinement seem much more tangible and much less hard to believe. One was lattice gauge theory, one was the 1/n expansion, and the other was the idea of confinement as a magnetic dual of the Higgs mechanism. If I think about it, of the three, the only one I really appreciated at first was the 1/n expansion. I struggled with each of the other two. So in the case of lattice gauge theory, the fact that a strongly coupled lattice theory is confining made confinement somewhat more plausible for sure. But it didn't seem like to get anywhere, you need to know that there's no phase transition between weak coupling, which you won't understand, and strong coupling that you do understand. It wasn't until computer simulations started to show that, which was by the end of the 70s, that to me at least, lattice gauge theory really seemed like a strong argument for confinement. The one which in hindsight most bothers me that I didn't appreciate it better in the 70s is the story about electric magnetic duality, the magnetic dual of the Meissner effect, but Houghton-Wilson operators. A lot of it sounded to me very vague at the time. So eventually, well, I feel that, but to be honest with you, in hindsight, I feel that was a limitation of me more than of what people were saying. Eventually, it became easier to understand what people had been saying. And of course, eventually we developed more experience with various kinds of models where you can understand confinement explicitly and get some kind of interpretation in terms of duality or topology or something playing a role. I noticed that in this conference, many of the developments that we've heard about involve modern twists on one of the three stories I mentioned from the 70s, which were lattice gauge theory, the 1/n expansion, and topological pictures, duality of the Houghton-Wilson lines, and so on. I personally found the discussion of the confining string particularly interesting. It suggests a limit. Actually, as Dubovsky explained in his talk, it suggests a limitation that the dream of a complete solution of large N QCD might be too much to hope for. And there are other things that also suggest that. We learned that the N=4 anomalous dimensions are part of an integrable spin chain, but the analog for QCD, for pure gauge theory, is really not. It's only asymptotically integrable. So it might be that what we have to hope for, well, implicit, what I'm saying is that well, we're all convinced confinement is true, but the dream is to find a more convincing, something more close to a pencil and paper proof of confinement, way of understanding confinement, as David put it, or solution of the confinement problem. The dream was that that would involve a solution of the large N, the string that's dual to large N QCD. The evidence now is probably we have to settle for a little bit less. Maybe to concretely understand that string, making confinement and a mass gap manifest, and maybe get a new computational method that gives some kind of asymptotic solution. Maybe an expansion of the mass levels at high mass. Anyway, you can, something like that is what I would be my optimistic hope now. For the question of what it means to prove confinement, personally, I think that the fundamental problem is confinement in the pure gauge theory. Especially because in the real world, we believe that quarks are in a sense a small effect spectators from the point of view of the confinement problem. So anyway, hopefully in this nice collaboration here, there will be some insights that will lead to this asymptotic solution of the confining string or something.
We have another half an hour. You go.
20 minutes, whatever. We get hungry.
So the schedule says 6.
Yeah.
So I thought we might have a discussion, questions from the audience. I just want to ask everyone a question about proving confinement.
Yes.
So, I mean, sure could perhaps answer this question. Do you believe that one will require new mathematical tools? And second, even though there have been various attempts to educate mathematicians that this is an important problem and they should help us solve it, is there a group of mathematical people who are trying to prove?
Well, I can think of one or two mathematically minded people, but there's not a community of mathematicians working seriously on the problem.
And do you think new mathematics that doesn't exist or new mathematical ideas?
Some kind of new ideas, but
But there could be. I mean, some of the advances in rigorous mathematical treatment of, say, conformal field theory were very different ideas than physics would have thought of. I'm thinking whether something like that might be necessary.
that's a good question. I don't think I have much insight to that. I generally have assumed that a rigorous proof is very hard to come by unless there's a qualitative picture is achieved. It's always possible to be wrong.
So I have a question. So in the 70s, a lot was made of the analogy between Yang-Mills theory and two-dimensional nonlinear signal models. And there's still no rigorous proof of the mass gap in the nonlinear signal model 2 dimensions. So that's an easier problem. I'm just
That's far easier because there's a clear physical picture.
right.
And there you could imagine doing it for large N. So I think if the effort of constructive field theory that existed a few decades ago had continued for another decade or two, there's a very good chance that problem would have been solved. I'm not saying that about QCD. QCD is a much tougher problem.
Okay, we want, any of you have questions for anyone else here? Or shall we just open it up? So, So one of the questions I asked, which nobody answered, was, could you imagine if confinement wasn't? Right. I mean, everything, you know, all. And what would, you know? I mean, in the end, it's an experimental question.
Well, first you tell us if you can imagine PCB not being corrected.
Well, I could imagine, you know, it's easy to imagine that asymptotic freedom is correct. And everything we simply we discover a 10 TeV, 20 very massive quarks. So at arbitrarily high energies, they're much on the couple.
I don't think one would describe that by saying asymptotic freedom wasn't correct. That's not that different from QCD being combined.
Now, QCD is a theory by itself without the rest of it. So there's nothing we know about the principle, any principle, I would say, that says there couldn't be, you know, another 10 families of quarks.
Let's say that.
Way below the Planck scale, where basically all of this, there's a reason to put it 100 TeV. Why not?
But it wouldn't change the confinement problem.
No.
We're grappling with.
But so that really, to admit that that could be wrong, that could be an experimental discovery, and I know what that how I would see that. How would I actually? But anyway, I just throw that out. Outrageous.
But you can imagine that perhaps confinement is incorrect and we need a new light particle that we haven't detected. We missed the experiments that is necessary for confinement. Given the lattice results, I think it's like.
I'm giving advice to the younger people in the audience, don't follow these.
So shy.
So I have a question for Juan. So in your last slide, you mentioned understanding the string dual of the confining, the understanding confinement, the dual picture of n equals to 1 triangles.
Yes.
So Yuan Nunes and Pavana and Strassler wrote down a supergravity solution.
Right. Those are theories that have n equal to 1 supersymmetry, but they have additional fields beyond just the gluino and the gluon. So I had in mind finding the dual of the theory that contains purely the gluons and the gluinos.
So I have a question. If we want to prove that Yang-Mills theory confines, will part of it be a rigorous construction that the mathematicians will be happy with of quantum field theory in general? This will be part
This
of
quantum field.
This is a particular example, but that could be, there are many quantum field theories.
Most probably don't exist.
Right. So there are many that do exist in lower dimensions. to zero theory in 60. There's a long list of theories that do exist.
Some have.
Some have been, but using mathematical physics. But there are theories that I think it has not yet been proven to exist mathematically.
Like gauge theory in 4 dimensions.
For example,
Just to have one that's relevant.
but the asymptotically free ones, not the. So proving that is an important problem, regardless of whether the answer would be confinement or not.
Well, they just have $1,000,000.
Yeah.
Well,
But is it really the same?
There's $1,000,000 actually requires proving the answer, not just that the theory exists.
But,
So this is really my
hard to
question.
imagine. that you think you could prove that it exists without a Pascal?
I think you might be able. In actual constructive field theory literature, people almost never prove something exists without proving it has a mass gap somewhere. However, in 4-dimensional gauge theory, that's going to be hard. And I can well imagine a proof that which it exists and only proves power law correlation functions. In fact, my guess is that would come first.
So as we heard, in some theories, we can understand confinement via monopole condensation in a controllable way. So do you think there's any way to extend that to the full space of 4-dimensional gauge theories? And if so, is confinement equivalent to monopole condensation?
No, I hope you would.
In an abstract sense, it might be the case that confinement is equivalent to monopole condensation. But as a useful computational tool, that's too optimistic.
What do you mean by an abstract?
Well, I can't give you the most general thing it could be, but one example of what it could be is that every confining theory would be continuously connected to one that you could usefully understand that way. That would be an example of what the Seiberg could mean. But it wouldn't necessarily be useful in our corner of the world in the pure gauge theory. Because that's the problem I was interested in. And it still seems like the most important problem.
What the possibility is within authority theories, which confine without having this monopole condensation, say without being connected in any way to a theory. And probably it's hard to imagine that, but I also don't know how to rule it out.
I should add that if you look at the theory which really confines with the one-pole symmetry, etc., then the monopole is not really that well defined. It's really well defined only near the transition point. Or if you have special situations like if the theory has a U1 and then you can identify the charges. But in terms of the non-abelian gauge theory, which is strongly coupled, the monopole does exist if you change the gauge group. But then you don't have confinement. So I'm not convinced that this is a if and only statement.
Igor?
I just wanted to say something that came up in the lunch discussion and sort of well known to everyone that so we have lattice gauge theory, right, which in the strong coupling expansion, the confinement is obvious. And then we just start, dialing the lattice spacing down, kind of numerical work for showing that it seems to be present, but that seems like a pretty well-defined setting for trying to.
There are phase transitions. You mean starting with a strong coupling?
Yeah, and just.
There are phase transitions. I mean,
Yeah, more concretely, the U1 problem exhibits the same thing. So you don't see that the Q1 is different than SUN. Both of them. are strong.
Right. But so there has to be, I think there was a paper by Tamboulis maybe 15 years ago which claim to follow this path. But I think for U1, it didn't show a phase transition. But still, there have been many efforts in that direction. So I can imagine basically following, coarse graining the lattice or something like that.
But you're talking about analytically.
Well, proving bounds or something like it, just showing that the area law doesn't wash out. I mean, we have the string tension, right? You start following the string tension, you just have to prove that it doesn't go to
There are
zero.
roughening transition, all sorts of.
Right. No, that's why it hasn't been proven yet, but at least it's a path towards. It certainly can, the string tension can be normalized to zero in some cases. For example, in this 1+1 dimensional adjoint UCD with a massless adjoint, it does happen to renormalize to zero somewhat surprisingly. But all signs are it doesn't happen at 3+1. So.
But question, so there were some comments again, that again, if there's a mass gap, or as Mette was saying, that Higgsing and confinement sort of are connected. But to me, still intuitively having a mass gap or knowing that something is in the Higgs phase, associating different physics to it, necessarily the confinement. So is this something that actually is intuitively understood as, or could it be something that one can prove, that having a mass gap or something can have a Higgs phase that.
Well, water and gas also intuitively look different to me. You know that they're continuously connected.
Right,
I
but
don't see
continuously
why-
connected. is
So
maybe
there
not
could be
quite-
one region of the parameters that it looks more like confinement, another region of the parameters that it looks more like Higgs. But since they're continuously connected, it could be somewhere in the middle.
Could be very
It's
different.
not, yeah, it's not that different than liquid and liquid gas transition.
But could one imagine sort of assuming, suppose that one was assumed a mass gap? What are things, what? 1, 2. Form of confinement.
Well, if you prove mass gap, I think you'll get $1 million.
No, but I'm just saying, so that, now I'm saying assuming. Would that make sense? That you make that sort of a starting assumption and then you try to draw conclusions
I
from
think
that.
almost every physicist in this room would grant you that assumption. Is a valid assumption.
You mean that the mass gap isn't a valid assumption?
Yeah.
But is it then obvious that confinement follows?
I don't think there's more to it than that. If there is a mass gap and
Well, there is for pure, I mean, by the way, the Clay prize was for pure gauge theory.
Yeah.
no quarks.
that's right,
And there's an order parameter, we know.
that's right. No, there it's very clear.
So maybe, are you asking about pure gauge theory? Pure QC?
Well, actually, is this really true about the Clay prize?
The Clay price is first of all the mass gap, not confinement. And secondly, it's the pure gauge theory.
But is it pure gauge of SUN or PSUN?
Should be SUN, but it should be.
The foundation, well, there's no difference between the mass gap problem with SUN and PSUN.
That's correct, but the confinement there is.
But the problem was the mass gap. The problem was-
And I think
the reason the problem was the mass gap is that it holds universally for all groups.
Yeah.
So it requires less explanation. Speaking as one who was on the board at the time.
well, you could also ask the same question about E8, which doesn't even have a center. And there should better
That's
be.
why the problem was the mass gap.
To deal with massless quarks, there is no mass.
With one flavor there is.
Anyway, the problem was for the mass gap. And pure gauge theory.
One comment is if there is no proof for many years in these inflationary times, I think right is losing its meaning.
So I have a, so how much coarse graining would be required from lattice simulations? To what extent should, I mean, one should push along this direction?
Well, rigorously, you want to push it infinitely, right? You have to.
But that is impossible, perhaps, even with quantum computing. So, I mean, there must be some criteria.
Yeah, I don't know what I'm talking about, but some kind of iterative proof. You can, I mean, some people claim such a proof.
Okay.
Yeah, numerically, people have gone already to 100 or more, lattice sites in each direction. That's very convincing, but the proof would presumably go to infinity.
Do you think that any string theory, maybe including basically string, but also more generally, should be described by a two-dimensional CFT on the world sheet? Or could it be that there are string theories that are more general than that?
I think the expert is behind you.
Well, I cannot speak simultaneously in two directions.
That's a good question, especially, let's say, when you have weakly coupled theories. What kind? Is it like a topological theory? Two-dimensional conformal theory. I don't know, maybe there are other descriptions.
Was it a surprise originally that worked this way, or somehow you thought that that should naturally be true, that the world sheet theory should be described by conformal theory?
I don't know. What kind of sorry, what kind? Well, it's not a surprise. Anyway, I can imagine. Well, many. Yeah, for example, membrane. I don't know if this algorithm more than manifold and excitations of these manifolds. It's how should I put it? We have some apparatus which get the particles interact so on, and it generates prescription for everything. That's the nature. But I have no.
Okay, I think people are getting tired. So why don't we call it a day? And thank the speakers.
There is the dinner outside, everyone.